Shana Zoteta, and welcome to my YouTube channel.
Now, you may be wondering what exactly I'm doing here, and to that, I have an answer for you. Today, I want to talk about nuclear reactors and nuclear reactions by proxy. Now, there are a couple notable things over here, such as this, which is a diagram of your usual nuclear fission reactor, and these two diagrams here, representing nuclear decay, or the energy released in nuclear fission, and nuclear fusion, which I'm going to explain in more detail later. But before I go into detail about that, I'd like to talk about one of the very many common misconceptions about nuclear fuel and nuclear energy. Now, nuclear energy is often looked upon as something that's very dangerous and very problematic, when in reality it's not that in the slightest. As for a matter of fact, nuclear energy is actually one of, if not the best, form of efficient, clean energy that we currently have, which is why it should be taken with better consideration than it is by mainstream media. The biggest fear, of course, being about nuclear energy is radiation, but the thing about radiation, well, yes, it can be powerful, it doesn't travel very far due to something called the inverse square law, which, if you've seen my other videos, you may have heard me mention before. For example, if this rock here was a nuclear power source strong enough to melt the skin off my face at 1 foot of distance, at about 30 feet away from that same nuclear power source, you could experience little to no effects from it whatsoever. And this is all because of the inverse square law, where nuclear radiation weakens exponentially the farther you get away from the object of radiation source. For example, whatever the radiative power is at 1 inch away from whatever radioactive source you're using, at just 2 inches away, that same amount of radiative power could be cut by about a quarter. But of course, this does not mean that radiation and radioactivity and nuclear sources whatsoever are perfectly safe, as of course there are tons of problems and dangers that come with them, but those dangers are greatly overcome and taken care of with modern technology, which is why the mainstream fear of nuclear power is kind of outdated in a sense. But with all that said, I'd like to go into more detail on everything over here. And to do that, I think it's time to move on to the lab. So I made my way back inside, bringing my whiteboard along with me as I made my way back to the lab. Unfortunately, on the way there, I encountered a little difficulty trying to get the whiteboard through the door, but thankfully I figured it out in time to begin my daily routine. I started off with my daily blood ritual sacrifice to the YouTube gods in hopes of more subscribers and views. I then had my usual jug of chloroform on the side before beginning my transfer of nuclear materials, which unfortunately didn't go over too well. Here it is! Anyway, here we have the diagram of a typical nuclear reactor. Now, in the nuclear reactor, we have a couple components. You see here we have those uranium rods, which are fueling the whole thing. Specifically, uranium oxide is used in typical fission reactors. Protons and radiation are thrown off from these rods, or more specifically neutrons, I meant to say, are thrown off, and the radiation hits into the other rods, creating a chain reaction as they break down via fission, which heats up the water, converting it into steam and powering a turbine. The steam then comes up, condenses into one of those big giant cooling towers, which are of course signature of all nuclear reactors, and the water is fed back with a decent amount of it, which also just goes back into the atmosphere as steam. And more water is fed in, and this cycle repeats and repeats, and that's how you have a nuclear reactor. Now, this of course is just nuclear fission, as there's another type of nuclear reaction known as nuclear fusion, which instead of breaking a larger atom apart into smaller pieces like nuclear fission does, nuclear fusion takes two smaller atoms and fuses them together into a bigger atom, which creates about 1,000 times more energy than nuclear fission does, which is why it's so much more significant now as we try to attempt to build fuel-efficient nuclear fusion reactors over the typical fission reactors. Now up here we have a diagram of nuclear decay or nuclear fission. We have your typical fuel, uranium-238, which decays into thorium-234 and helium, along with alpha particles that are thrown off by the process. But of course, that is just nuclear fission. There's another process, nuclear fusion. Now, the two usual fuels used in nuclear fusion are deuterium and tritium, which are isotopes of hydrogen. Now, whilst the typical hydrogen atom contains one proton with one electron orbiting it, deuterium, for example, contains a proton and a neutron with an electron orbiting it, and tritium contains two neutrons and one proton. Now, this doesn't actually change what element it is, since the factor that changes the element is how many protons it has. The amount of neutrons is kind of insignificant, and because of that, you can get specific compounds which have more neutrons than their typical element would have. Now, in nuclear fission here, we have a deuterium atom and a tritium atom, which are pushed together by an immense amount of force, which releases a large amount of energy, a neutron, and a newly formed helium atom. So those are the key differences between nuclear fission and nuclear fusion. Fission is breaking apart a larger atom into smaller ones, and fusion is fusing two small atoms into a larger one, with some other results as well via that combination or deconstruction. Now, whilst I have discussed the functions of a nuclear fission reactor and how that generates energy, I haven't actually talked about how a nuclear fusion reactor generates energy and what that actually looks like. And with that, I think it's time we move on to the next part. So I tried to buy some human bones from the fine Chinese sweatshop, but was unfortunately rejected. So I simply just waited till nightfall. After that, I ventured out into an undisclosed location to retrieve some small amount of human remains. Now, the reason I want them is to do some radiocarbon testing on it for the video that I'm doing here, to show how radioactive decay can affect the age of the material. I then attempted to test it, but unfortunately electrocuted myself in the process. Anyway, now I'm going to go over nuclear fusion reactors and how specifically they function adjacent to nuclear fission reactors and what's different between the two. Now, one of the biggest issues with nuclear fusion is that it takes an immense amount of energy to actually get two atoms to collide with each other and to fuse. This needs to occur in an environment that's very high pressure and high temperature, which is one of the reasons why nuclear fusion reactors haven't really been perfected yet, since the temperatures and pressures required are so intense that it's very hard to simulate here on Earth. Now, unlike nuclear fission, where those very large radioactive molecules will decay naturally on their own, nuclear fusion will not just happen in your standard environment. It needs very specific conditions to occur. And that's the big difference between nuclear fission and nuclear fusion. Now, the sun is an example of nuclear fusion. The sun performs nuclear fusion, being made majorly of hydrogen and helium. The helium being generated by the process of nuclear fusion between the two hydrogen atoms colliding together and fusing. And then, of course, a byproduct of that nuclear fusion process is light and heat, which we receive here on Earth, and so does every other planet in the solar system. So, in summary, nuclear fusion is the combination of two smaller atoms into a larger compound, releasing a substantial amount of energy, and nuclear fission is a much larger atom, breaking down into two smaller atoms, releasing radiation energy as well. Nuclear fission, whilst is efficient and does work in nuclear fission reactors that we have today, is not anywhere near as efficient and effective at creating energy as nuclear fusion is, which is why there's a major push to create an energy-efficient fusion reactor, that way which would unlock essentially almost unlimited energy for mankind, which is obviously why it's so significant. But anyway, with all that said, that's pretty much it. I hope you enjoyed the video. Remember to like and subscribe. That's pretty much it.